Hello guys, I hope you all are doing great. So today we'll be learning about magnetic flux and then we'll study magnetic flux density in detail. We'll study about the basic concept that is being implemented in this scenario of magnetic flux. So to firstly understand what is magnetic flux, you first need to consider a magnet. Let's say this is a magnet and this side is the north pole of the magnet and this side is the south pole of the magnet. And let's say um, the field lines of the magnets is towards from north to south, and we know this thing that field lines are always north to south, so we'll just reconsider that basic concept. So just suppose that these are the magnetic fields. Now to understand the concept of magnetic flux, you need to again consider a specific area. Let's say this is a area. So the relationship between this area and the magnetic field lines is known as the magnetic flux. What we need to do, we will keep this specific area within the magnetic flux, within the magnetic field. Let's say we kept it perpendicular to the magnetic field like this, somehow like this, and now number of the magnetic field lines will pass through it, right? Let's say that this much number of the magnetic field lines have passed through this specific area. So this is known as the magnetic flux. The number of line passing through a specific area, the number of the magnetic field lines. If we talk about electric field, so the concept would be same, but what will alter the magnetic fields with the electric field, and now we'll consider the electric field, number of electric field lines and passing through a specific area. This is known as electric field flux, but here we are considering magnetic field, so we have just kept a small b under the flux, under the phi. This is known as phi. We pronounce it as a phi. So this phi is actually equal to the product of b. Let me just write first b into A presents here the area and B presents here the magnetic field lines. Now, if you have studied the chapter vectors, so I hope that you know the concept that here the magnetic field lines are uniform. That means it have a specific direction. There's a uniform flow of magnetic field lines. And we know this thing as well, that area is a vector quantity. So the relationship between the B and A will be a dot relation. So we could also keep here the cos theta, because dot product states the cos theta, studies about the theta that is cos, and alternatively the cross product, dot product, studies about the sine theta. So this is the basic concept of the magnetic flux. Now let's study about few things about few concepts of it, where the magnetic flux is maximum and where the magnetic flux would be minimum. First, you need to keep one factor in mind, that we are using theta, that is in the cos value. And we know that a cos lies on which axis? On the quadratic system, the cos actually lies on the x-axis. So here, if an object lies on the x-axis, so that specific theta is at the maximum. Or you could say that theta when is equal to 0 or 180, so we call it as maximum. And if theta is equal to 90 or 270, so we call it minimum. Now how this concept is actually being applied, let's study about that. We know this fact that here the area, let's consider this is a area, and now this area is actually phasing the let's say this is the magnetic field lines. I'm viewing it from this point. I'm just standing in front of the North Pole, and now the magnetic field lines are causing by me as well, by the way. So here, let's say that initially I've kept the this specific area just parallel to the I've used the word parallel to what? To the magnetic field lines. That the value, the theta between the magnetic field lines, here you could see these are the magnetic field lines, and this is my area. The phase of the area, the vector, the arrow of the area is also facing towards the South Pole. That means the direction of the magnetic field lines and direction of the area is at 0 degree. Both are facing same way. But what if now I need to first remove this vector. Just give me a moment. Let's say um now I'm rotating. I kept it like this, right? Now I'm rotating my area, and now my area is somehow like this. Now it's at the now it's facing actually the direction that is perpendicular to the or at the 90 degree. This is the direction of the what? This is the direction of the magnetic field lines, and let's say this is the phase of the surface. Alright, now the surface and the magnetic field is making the degree 90. So in that case, now here consider how many lines are passing through the surface. So in this case 0 lines will pass through the surface. So this sort of thing is known as the minimum value of the magnetic flux. I hope that you get it, and now let's move on to the next concept, that is unit of both of these things. So here we actually measure the magnetic flux in Weber, which is equal to Newton meter per ampere, and here 1 Weber is equal to Newton meter per ampere. I hope that you get it, and this is something that you need to learn. Let's move on. Okay, well, one more thing. Maybe it can be asked from you that how we got Newton meter per ampere. So we have studied a formula that force being applying on the magnetic field is equal to BIL, and we have studied this thing. According to the first Ampere's law of the magnetic fields. Now, if we want to know the formula for the B, so we'll keep B here, and it will become F upon IL. Force is what? Force is Newton, and we know that I is equal to what? I is equal to change in current, that is also denoted by ampere, and it is being multiplied by m, which is what? The length. So in that case, oh, sorry for this, sorry. Now the actual formula is what? The B, the value of B is being multiplied by area. Now we know this thing, that what we just studied, that B is equal to Newton per ampere into meter, right? And we know what the area is equal to meter square. So here 1m would be cancelled out with 1m, and now we'll get the formula Newton meter per ampere. So somehow indirectly this is also in force into a length upon somehow it could be considered like that. So this is something that we got, or you could just leave this for a while, and I hope that you understand the derivation of the formula that I did. Okay, moving on to the next topic of our lecture series, that is, I think I should increase the weightage. That is the magnetic flux, and then now we are going to study the density. Okay, initially, if you have gone through the basic concept, that what is actually the density? So we got to know about the concept that density is equal to mass per unit volume. That means dm, the mass, that object that is moving or is actually placed in a specific area, so we need to measure that mass with respect to that surface. This is known as the density. Now the same concept of the density would be applied here, but here we will keep a really minute difference, that here our density, the B, would be equal to force that is being applied per unit I into L. This is the formula of the density, and we denote density by B, by the way. So here the current that is passing through, and the current is being multiplied by the length. Somehow this is the magnetic field, so multiplied by the force applied to the surface because of that magnetic field line. This is known as the magnetic flux density, or you could also consider it as the maximum number of lines passing through a surface. This is called the magnetic flux density. So I hope that it is clear to you. And now moving on to the formula of, the unit of the magnetic flux density. So we consider density by a unit that is Tesla, and Tesla, 1 T is equal to Newton per ampere dot meter. This is 1 Tesla, which is equal to this. So I hope that today's lecture is helpful for you, and thank you so much for watching our video. Stay tuned for future videos.